Good afternoon, everybody. Thank you for the nice introduction, Fernando. Indeed, I am Jeff Verbeek from Vito Energyville, and I am guide you through a presentation on flexibility assessment, determining the flexibility potential of industrial plants. And I gave the presentation or the webinar the quite ambitious subtitle, Demand Side Flexibility Business Case Estimation Made Easy. It is up to you to judge at the end of the presentation whether we succeeded in that or not. At least it's our ambition and goal to make this easier. Okay, Fernando already introduced the project a bit. I had foreseen that as well. So we want to use the flexibility potential in energy-intensive industries to further facilitate the growth of variable renewable energy sources. It is a Horizon 2020 project. You see the partners here all at the bottom of the slide. It's we are 8 partners, and our focus industries, when we were writing the proposal, were the chemical industry, non-ferrous metals, steel industry, cold storage facilities, and water treatment plants. In the meanwhile, we learn, and we have seen that a couple of other ones are interesting as well, as for example the paper industry, which is very energy intensive as well. Within the project, we try to cover the following target countries: the UK, Belgium, Germany, France, Italy, and Spain. Good. Let me give you an overview of what you can expect in the next, let's say, 40-45 minutes. First, I'm going to quickly introduce you to demand response. Actually, I guess everybody knows what it is about, but a reminder can be convenient. Then, how do we calculate a demand response business case, and why do we see a need for a simplified methodology? Then I guide you through the simplified methodology as we developed it during our project, step by step, and I'll show you an on-site renewable energy business case as an example. And then I hope to end with some nice conclusions and discuss the further steps we are going to take in our project at the end of the presentation. Good. Let's start with the context, demand response. I think everybody is aware that our electricity system changed significantly over the last, let's say, 5 to 10 years. In the past, everything was relatively easy. You had a traditional generation unit, you had lots of customers, you had a grid in between which was mostly unidirectional. It was very simple to organize. But with the upcoming growth of renewable energy, a couple of things are changing. We see them everywhere, the wind turbines, the solar panels, which I think is a very good idea, but there might be some issues every now and then. I'll show you a tiny little example. On a day that the wind starts blowing and the sun starts shining, you can, for example, have grid congestions. The grid is suddenly used in a way we are not, where it was not designed for in the past, and issues can occur. One of the possible ways to solve this is, instead of trying to control it from the production side, is to control it from the demand side by, for example, in this particular case, switching on additional flexible load, a load which can be switched on, which can absorb the excess energy at that moment in time. This is only an example. You know, you can use demand response in a multitude of ways, and we'll come back later to that later in the presentation. Don't worry, we don't focus only on wind turbines and solar panels in a demand response context. And of course, I put it at the bottom slide there, you know, demand response is seen by the European Commission as a very important tool in order to cope with the further growing of the renewable energy at the moment and in the near future. Okay, that was my little introduction on demand response. Let me introduce you now to the traditional way how we calculate demand response business cases. and you'll see soon that it is not always as easy. The first thing you have to wonder or to think about is, if you want to motivate industries to actively participate in the electricity market, yeah, they would like to make money with that. So you need to have business models in place. In the industry project, in the first stage of the industry project, these business models have been investigated very thoroughly. For this simplified methodology, we simplified it a bit, and at the bottom of the slide, I put the main categories of business cases, business models you can use for demand response. The first one is standard contract optimization. It's the simplest example. Even at household level, you could do something like that. Basically, if you have a day tariff and a night tariff, and you can move a bit of your electricity consumption from the day to the night, you can make money. The second one is a bit more oriented already to SMEs and big industry. Day-ahead optimization. If you buy your electricity on the day-ahead market, which has to be settled every day, you have a very variable electricity price. So again, if you can buy at a cheap moment and you can reduce your energy consumption on the expensive moments, again, you can make money. The most used way of the most known way of demand response in industry at this moment, definitely, I think, is reserve capacity. Lots of big industries already offer reserve capacity to transmission grid operators, either in fast reserves, so the frequency containment reserves, in the restoration reserves, or in the replacement reserves. Typically in the past they were called the primary, secondary, and the tertiary reserves. Then there's still a possibility to trade on the imbalance market. That's the fourth option. And the last one is on-site variable renewable energy optimization. That's maybe a bit newer for you, but it's one we always explicitly mention in the industry project because we think it's one of the very good ways to use flexibility, and I'll come back later to that, how that might work. What you see as well is that these business cases might vary a bit from country to country. Wait, I go to the next. Okay, I'm being too fast. Okay, a second thing is regulation. We have made a list of business models. You see all our target countries. Not every target country implements EU guidelines as fast as the other one. So you see in some countries things which work already very well get a green dot, while in other countries, for example, it's not even legally allowed yet. So there are quite some differences which are nicely listed within the project. In Work Package 2, we have investigated that thoroughly and listed up what the status in the different target countries is. Then a third thing, if you want to calculate a business case, it is very important that you have price information. Most price information is publicly available. For example, day-ahead prices, historical day-ahead prices can be downloaded from websites. Most reserve prices can be found on websites of grid operators. That's the easy bit. But if you want to do, for example, calculate a business case even for a standard contract optimization, it already gets a bit tricky because it's based on bilateral price negotiations between the customer and the electricity provider. So if it is red in this graph, does that mean we can't calculate a business case? No. Of course we can calculate a business case, but we need to see in detail how the contract is set up. It is very difficult, let's say on a academic level, at a top level view, to estimate what the value could be. So that's the reason why we distinguish between green and red. Orange means that within our consortium we have a quite good feeling what in reality the prices are, although they are not known publicly. Good. A fourth thing, and that's maybe one of the most tricky things, is you need a kind of flexibility model where you can start your calculations with. You know, most industries you walk in, you see lots of buildings and machines and all have their power consumption, but that's not the good starting point. You have to simplify it and try to describe the relationship between the different processes in the plant in a bit of a mathematical way to the extent that it is relevant to make your business case calculation. I'm not going into the details during this webinar, but it's one of the trickier things in a business case value estimation. Good. Once you have all these four things for the different countries, you can start calculating your business case. And what you see in this graph is I added now little abbreviations in the table below, is the way how you calculate a business case. So in one of the tasks in the project, we have really looked to the different countries, to the different business models, and tried to clarify how many different optimization methods, how many different calculation methods you need to be able to calculate all the business cases. So what you see basically in this table is the summary of the previous task we did in the industry project, making up basically a status of how you in a traditional way would calculate a business case for demand response. Good. Now it is time to discuss why there is a need for something more simple. The first issue we see is that the skills needed to create a flexibility model are quite widespread. We at Vito Energyville already perform this kind of audits and support to industry for the last 5-6 years. And at a couple of moments in time, we have been approached by consultancy agencies, by engineering companies with the question, yeah, we would like to learn to do that. And what we see in practice is that they are very good at the first stage of the flexibility model in the first stage of that process, meaning the selection stage. You have to go on site, you have to look what's there, you have to have a good top-level understanding of the industrial processes which are going on the plant, of course with a good focus on the energy flows, but typically engineering companies, consultants which are already in the industry are quite well capable of identifying this. But then comes the tricky bit, the modeling stage. Suddenly you have to translate all of this into a rather mathematical model which describes the production process to a certain level, all the constraints, what's connected, what's not connected, what's possible, what's not possible from an energy consumption point of view. And that requires quite some understanding of modeling and optimization techniques. And the combination of these skills is not so obvious in many cases. That's the first thing. A second thing, the business case calculation complexity varies. There are a couple of cases, I am exaggerating now a tiny little bit, a couple of cases you take a piece of paper and your calculator, and you can nearly on a piece of paper calculate what the value is you are going to get in some cases. But in most cases it's more complicated. Oops. Fernando, I pressed on my spacebar and my screen is gone.
Yes, let me upload again. One moment. Yeah, here it is. You can go ahead.
Thank you very much, Fernando. It's a PowerPoint habit, and this is not PowerPoint. I tried not to do it again. Okay. Quite a couple of other cases, you can still calculate with a spreadsheet. And I have people seen doing it, have colleagues seen doing it. They're really clever people and they can do amazing things with Excel. But at some point, even the most experienced Excel users admit if you really want to do good business case calculation, you need real optimization tools, real optimization software. In the right corner, I put a couple of software tools which are quite well known in the optimization world, but which are not always within the tool set of engineers and consultants in the industry. So that's a second issue, that most people don't know these tools very well. So that brings us to the third thing, is how accurate does a business case value estimation have to be? What we have seen by experience is that building up interest in demand response in many companies, it's a long, time-consuming process. And typically, it starts with a couple of people which are really believers of it. They need some numbers to get going, and once the seed is planted in the company, slowly it can grow. And what's the issue is that if you want to give these believers a rough estimate, you don't have the budget yet to do a full-blown audit of the industrial process, but a rough estimation is maybe enough to get things going into that company. And that's the reason why we strongly believe that if you can come up with a simple way to have a rough estimation, that you can really make a step forward in making demand response accessible. So let's write down a couple of requirements we have for our simplifying tool. The first one is we want to have something which is cost effective and time efficient. It shouldn't take too long. A site visit, a bit of calculations in the office, writing a little report. It should not take too long. Very important. Secondly, as explained in the previous slide, an order of magnitude accuracy is in many cases enough, especially if you want to plant the seed. That's enough. It is more important that it is cost effective and time efficient, if that goes a bit at the cost of the accuracy. And a third thing is that, and that's a very important one, we don't want the use of specific modeling and optimization tools. Good, those are the requirements, and that's where we started with to think about a simplified methodology. And that's what I'm going to explain you now, step by step, how we approach this. Good. This is a bit of a funny slide, maybe. It's a very naive approach. What you basically do is, what you could do, we didn't do that, but what you could do is like, yeah, you do lots of full-blown audits, you put them all in a database, and if you have plenty, at a certain moment in time, you can nearly pick one which is very similar out, and that's more or less the value. Okay, it's going to be a very time-consuming process to do this way, but you understand the advantage is you don't have to do the calculations yourself. They are already pre-calculated in your database. That pre-calculated concept we are going to keep in our simplified methodology, but we are going to try to do it a bit smarter. We are going to do 4 things. We are trying to do a mapping exercise. We are going to normalize, select, and scale. It sounds maybe a bit abstract at this moment in time, but I'll guide you through these 4 steps. Let's start with the mapping bit. Okay, what I have drawn on this slide is a very simplistic view on a battery. We call it the generic battery model. Basically, what is a battery? A battery is a box where you can put energy in. So you put power in and the energy level increases. If you take power out, the energy level decreases. Very simplistic, no losses, very fundamental. If you think very carefully now, this looks already a bit more like a real industrial process. What you see in this figure is a part of an industrial process. At the left-hand side, you have a machine. You put power in, and it produces some product, whether it be cookies or rubber or polypropylene pellets or whatever, doesn't really matter. But it is put in a buffer. And the buffer is there to disconnect the process at the left-hand side from that one at the right-hand side. The process at the right-hand side then takes, again, the product, the cookies, the rubber or whatever, out of the buffer, and the buffer gets emptied again. If you think really carefully about it, and you make a bit of abstraction of it, actually, this buffer is exactly the same as that battery model. You can increase the speed of the left process. That's basically storing energy in the buffer. Every product you put in your buffer has cost a certain amount of energy. And at the right-hand side, you take the energy out again. I can't explain it in detail in this webinar, but in the document we have written and which you can download on the industry website, we nicely explain really numerically that the behavior of a generic battery model or a buffered industrial process are actually exactly the same if you make a couple of conversions. Another example, maybe if you're not convinced yet, is a CHP with a hot water tank. If the hot water does not stay too long in the tank and you make abstraction of the losses of the tank, this is again an energy buffer. So that's the first thing we are going to do. We try to find a limited number of reference processes and then map real industrial processes on these simplified reference models. That's the first step. Okay. That already makes things a lot easier. So I only have to make lots of business case simulations with my reference models in my database. A second thing is we can normalize quite a couple of things. It's a bit of a joke here, but if I can earn 20 euro per year by trading electricity on the day-ahead market with my car battery, which has an input power of 2 kilowatts and an output power of 2 kilowatts, and it can store 1 kilowatt hour of energy, yeah, I don't have to calculate that for 20 batteries because it is very obvious. With 20 car batteries, I can earn 20 times that amount. So that's 400 euro. So that's a second step. If we normalize our reference processes, there are some scaling rules. Some things scale very well, some things don't, but also that we try to put in the document under which conditions you can scale, but it eliminates a lot of pre-calculation work. Another example where you can use normalization as well is in the price setting. If you take a business case, for example, where you have try to shift electricity from the day to the night, and you have a price difference between the day and the night tariff of 15 euro per megawatt hour, and you can make 2,000 euro per year with that, well, it is pretty obvious again that if the price difference is 30 euro, you can double your the value to 4,000 euro per year. That's another form of scaling which works very well. The third step is selecting. That's a bit more tricky to explain, and the first couple of slides you're not going to understand why I set select there, but don't worry, it will become clear why I called it the select step. I'm going to show you a very simple example of how an optimization tool works. This is the day-ahead electricity price for one day, and you see in this graph that the electricity is cheap in the middle of the night. It's like 10-15 euro per megawatt hour. The most expensive moment is at 5 o'clock in the afternoon, so that then it is above around 70 euro. And the trick is, of course, if I have a battery and I want to make money on the day-ahead market, I try to buy electricity at the moment that it is cheap. That's what you see in this graph. I can take the pointer here. So if here you see the moments where I can buy electricity. Then, of course, it is the next trick to sell it when it is very expensive. So at these moments in time, the electricity price is relatively high. So that's the ideal moment to sell the electricity. And of course, I have to do that within the boundaries of my battery. So I cannot exceed the maximum energy content of my battery, which is maximum 1 megawatt hour in this case, and it cannot go below 0. And further, I don't want to fool you, so I start with a half-charged battery, and I start with a half-charged battery, and I end with a half-charged battery. So the optimization tool chooses these optimal moments to charge and discharge the battery, and you can prove that in this particular example, you can make a profit of 66 euro with a 1 megawatt hour battery, which has a power input of 1 megawatt and which can inject 1 megawatt into the grid. If you do the same exercise with that same battery, but for the whole year based on historical day-ahead data, in this case it was for Belgium, you can make a profit of about 19,000 euro per year. Or, and that's what we actually really like, is we gonna express it as an average. You can, on average, make a profit of 2.2 euro per megawatt per hour. Where does the megawatt suddenly come from? Well, I explained to you before that scaling rules apply. So if I double my battery, so I have a 2 megawatt hour battery with 2 megawatt input, 2 megawatt output, I could make a profit of 4.4 euro per hour. So that's what we call normalization. So the normalized price is 2.2 euro per megawatt per hour. An additional advantage of express it in this unit is that quite a couple of TSOs, for example Elia in Belgium, express their flexibility prices as well in euro per megawatt per hour, and that makes it way easier to compare all the business cases. Okay. Unfortunately, if I only double the battery size, but I do not double the input and the output power, that doesn't scale very nicely anymore. But that doesn't mean that then I can do other things with it. And that's what we are going to do. We are going to put it in a graph. That's what you see in the next slide. In this slide, I'm going to get the pointer again out. Here you see the business case I explained to you earlier. So for a battery size of 1 megawatt hour, we can make a profit on average of 2.2 euro per megawatt per hour. If we double the battery size, but we keep the input and output power the same, so a 2 megawatt hour battery, the price does not double, but it is 3.68 euro per megawatt per hour. And so we scan from a very little battery size to a very large battery size. We do quite a lot of business case calculations, which ends up in this nice graph. So how do I come to the name or to the term select? Well, it's very simple. For example, if in your particular case, in your normalized business case, your battery size is about 10 megawatt hour, you select the right value here in the graph, and you'll see it will be approximately 7.3 euro per megawatt per hour. You select the right value in the graph. That was step number 3. Step number 4 is scale. That's very simple. It's scaling back. We did an exercise in a normalized world, but we want to do a real business case. So at the end, we have to scale back to the original values. It's a bit like we looked in the graph of one battery, and we have to extrapolate it what it would be if it would have been 20 batteries in real life. That are the 4 steps. I put them all in a summary here in a more graphical way. So we go through it again. You start from a real industrial process. The first thing you do is find a reference process process which maps the closest to your real industrial process. The next step is you normalize everything to a 1 megawatt equivalent. And for the 1 megawatt equivalent, we pre-calculated a whole bunch of business cases in so-called normalized business case graphs. Typically, what you can expect is that you on the x-axis here, you see the different business cases. I indicated it here with on the x-axis the different business cases, and here on the y-axis you have to make this graph for all your reference processes you have in mind. Maybe I should have added like a third axis, which would be all the different target countries within the project. So what you do is you pick the right normalized business case graph for the right reference process and for the right business case, in this case the red one, and then you have the normalized business case value, and in the last step you scale it back to the correct business case, to the real process values, and you have your correct business case value. Good. I hope you understood more or less how this could work for day ahead price optimization. Maybe one which sounds a bit trickier, but which is very relevant for our project, is how can you do that now for on-site renewable energy business case? And that's what I'm going to explain you in the next section of the webinar. We consider the following configuration. We consider a wind turbine and a industrial estate which are connected to each other behind the meter. You see at the bottom you see the meter which connects the two together to the electricity system. And unfortunately not in every target country, but in Belgium for sure, this results in a pretty interesting business case. Why? I'll explain you. At very low wind conditions, or at wind conditions, the industrial estate can buy electricity directly from the wind turbine without paying transmission grid fees, distribution grid fees. Also some levies don't have to be paid. So that makes that you basically pay only for the commodity, and a bit of there is a bit of charges on top of it, but it is not an awful lot. So in the example I'm going to show you in the next slides, we assumed, it's just an assumption, that you can buy electricity from that wind turbine directly at 40 euro per megawatt hour. At low wind conditions, of course, the industrial estate has to buy extra electricity from the grid, and that will be at the normal price. We assume that it is 100 euro per megawatt hour. What happens now at very high wind conditions is that the industrial estate can still run on wind energy, but it is possible that there is excess wind energy, and that will be fed into the grid. It is assumed that there is no cost for the company on that. It depends a bit from case to case. There are definitely cases which you can find where there is an agreement between the wind turbine investor, the industrial estate, and the electricity provider where this is possible. How are we going to fit in our generic battery model now? Well, we assume that the industrial estate consists of two things. We assume that it consists of a generic battery model, the thing we have been discussing already for quite a while now in this webinar. You see it here. But we assume as well that there is a inflexible load. The inflexible load represents basically the base load of your company, the load which is more or less all the time there. Of course, I know in practice it is not always constant, but for the sake of simplicity, in this case, we assume that this inflexible load is more or less constant. What will happen now in practice is that when there is excess electricity available, you start charging your battery. When you have to buy expensive electricity from the grid, you discharge your generic battery model again. This does not mean, however, that you physically need a battery in your plant. Of course, this can be an abstraction of a physical process, the example I gave you before with the buffer which contains I don't know, rubber cookies or polypropylene pellets. By doing so, you start making the same optimizations again, and on the horizontal axis you see again the battery capacity increasing from very small battery here to a big battery there, and you see that the value you can achieve is in the range between 25 cents and €4 per megawatt per hour. Very important to mention here is that this graph is made for a fixed load of 0.2 megawatts. And that's quite important because you will see in the next slide that if you change that fixed load, that this graph will change significantly. In this graph, you see 6 plots on top of each other. It's a bit messy, I admit. I didn't build it up properly step by step, but I think you'll get it. The green one is the original one I showed you in the previous slide, which is for a fixed load of 0.2 megawatt. The blue one is the 0.3 megawatt, the fixed load of 0.3 megawatt, so that is higher. And then suddenly something funny happens. When you increase the fixed load to 0.4 megawatts, my business case starts dropping. And it drops very fast because here it is at the light blue one, it's at 0.75 megawatts, and at 1 megawatt, no business case anymore. Actually, if you look at it from a more intuitive way, it's easy to understand. At the moment that your plant consumes more electricity than the peak power of your wind turbine, you can absorb absolutely all electricity from your wind turbine, and you don't have a business case for your flexibility anymore. Now, it gets a bit more interesting if you plot this information a bit differently. What I did in this plot contains exactly the same information as the previous one. The only difference is I put the inflexible load on the x-axis, and the value is still on the y-axis, but for different battery sizes. And what you see happening now is that there are really optimal points to find. Here you see that around, when the fixed load is between, let's say, 0.2 and 0.3 megawatt, you have the best business cases when you combine renewable energy, in this case a wind turbine, with local optimization with industrial state. Now, why do I show you this? Because these normalized business case graphs not only help you to solve to calculate your business case, but we are quite convinced that these will be a help in the future when design for flexibility will become more and more important. This kind of graphs will help you very much to see which ratios are really optimal to make the most of your flexibility in the company. Then we are nearly at the end, so some conclusions and some further steps I'd like to discuss with you, and then we're done. First question we can ask ourselves: have the requirements been met? I remind you the requirements we had beforehand. Is this method cost-effective and time-efficient? An order of magnitude accuracy estimation is good enough, and no specific modeling and optimization tools are needed. And we're going to be really, I'm going to be really honest with you. I think there is one assumption: under the condition that your industrial process can be mapped on a relevant reference process, the approach we presented to you is pretty straightforward and definitely does not need any specific modeling and optimization tools. So from that point of view, I think we managed to find a way to simplify the business case calculation methodology. I already put the question here before you ask it, but it is really going to work for complex cases, which is of course a very relevant question. I would insult quite a couple of industrial plant managers probably by assuming that you can just map a complex chemical production plant into a simple battery model, and you're absolutely right, that's impossible. But you have to keep one thing in mind. I made a little graph here where I, in a simplified way, try to represent an industrial process, and industrial processes are always very interconnected, different processes linking from one to the other. And assume now that there is flexibility in process number 4 and in process number 6. What you can do with this methodology is you calculate the business case value for process number 4, assuming that it can operate completely independent of all the rest. And you do the same for process number 6. And what you can assure is that the business case value you achieve when everything operates all together, that business case value will always be, the maximum value you will get is the sum of both or lower. And of course, that's not an answer to the question, what's the real value, but at least you can give an upper boundary for it. What we see in practice is that when we enter a company and they need our help with trying to assess the value, quite often they overestimate the value. So if the sum of two simple things still not answers there is not enough to really make steps forward in the business decision process, well, I can assure them that if you do the calculation really properly, it's even going to be worse. So from that point of view, it's still a very helpful number you achieve with the methodology. Good. A couple of next steps. The methodology has been developed the last couple of months within the industry project, and one of the next steps is that we are going to perform a number of case studies. In these case studies, we are going to do a full demand response audit and see whether this simplified methodology will work in practice. These case studies, the selection has been taken place already, will happen, let's say, from now on till mid next year somewhere, and we try to spread it out over the industries and over the different target countries. And then I'd like to invite you to further steps we are going to take with this methodology. You know, this webinar is a first information session where we, as a teaser, want to show you what the potential of our methodology actually could be. In the middle of 2017, we will organize a real hands-on workshop. At that moment in time, we'll have a bit more experience in practice with it. We will have tested it in the different case studies. So if you are still interested in the approach we have been presenting today, please subscribe for the hands-on workshop. It will be organized somewhere mid-2017. The date is not fixed yet, but for sure we'll keep you informed when it will take place. And it is the methodology, it is important that it is a part of the project that we try to bring this methodology to the market. So the uptake by the market is an important element in the project. So, and this is a question to you. If you are an engineering company or a consultancy agency with experience in energy services, or you are a BRP or a balancing service provider or an aggregator, and you are interested in extending your portfolio with a cost-effective demand response business case advice, or you are yourself an energy-intensive industry and you want to understand yourself how your demand response opportunities, what they are in your company, or for whatever reason you're interested in this methodology, we would like to hear from you. Please contact us and we can see, we will keep you informed and explain you in further detail what we can provide you, how the methodology works and how we can proceed from here basically. These are the contact people within Vito Energyville, myself, Daan Six, the project manager locally for the project here at Energyville, and Steven van Deun, our business development person at Energyville. Or, of course, if you know other people within the industry project, contact them and they'll forward your contact details to us and we'll contact you. That was my introduction to the simplified methodology for business case calculations on demand response. And the word is